What we have here is an achromatic lens triplet using BK7 and SF10 glasses. This lens has a diameter of 15 millimeters, is roughly 1¼ centimeters long, and has a back focal length of 40 millimeters. This design was optimized over 3 wavelengths from 486 to 656 nanometers and over 2 angles, 0 degrees and 2 degrees off-axis. If we look at the focal drift plot for this design, we see that between 450 and 700 nanometers, both incident angles have a focal shift of roughly 120 microns. What we'll be doing today is taking this triplet and replacing it with another lens to reduce its size, weight, and power. That is, we'll be doing a SWaP reduction by replacing this triplet with a smaller GRIN singlet. To start creating our GRIN singlet, we will open up GemSif and create a new system file. To do that, go up to the File menu and select File, New System. Or we can go to the model hierarchy here on the left, right-click the application node, and select New System. Then we will create a reTORT simulation by right-clicking on the system node and selecting New Simulation, reTORT. We could also do this through the File menu by selecting System, New Simulation, reTORT. Now let's configure our source. If we look under the Sources folder underneath the reTORT simulation, we will find the default beam source. Select the beam source object to display its property editor here on the right. By default, only on-axis ray bundles are generated by the beam source. To add an off-axis one, let's add 2 degrees to the end of this list of incident angles. If we look at the default optical spectrum beneath the beam source, we see that it already contains the wavelengths we are designing for, so the default spectrum is good. Now let's create the gradient index material we'll be using for our lens. Our GRIN material will be a mixture of 2 glasses, so first let's import those glasses. Right-click on the Materials folder and select Import Material from Database. In the window that pops up, select Glass, BK7, and we'll pick the one from Shot NBK7. Then click Import. We'll follow the same process for the second glass. Import material from database, glass, this time we'll select SF10, and again we'll pick the one from Shot and SF10, and import. To create a GRIN mixture of these glasses, right-click on the Materials folder, and from the Polynomial Material Mixtures library, select New Cross-Polynomial Binary Mixture. In the Mixtures property editor, set Material 1 to BK7 and Material 2 to SF10. These C0 through C11 properties are polynomial coefficients for the mixture, and use a combination of radial and axial terms. This polynomial does not specify the refractive index of the GRIN, but a mixing fraction that determines how much there is of material 1 at any point in the lens. If this polynomial evaluates to 0, it means there is 0% of material 1 and 100% of material 2. If the mixing fraction is 1, it means there is only material 1 at that point and 0% of material 2. Of course, if the polynomial evaluates to something outside of 0 and 1, then that's an impossible mixing fraction. Not to worry though, the optimization wizard will monitor the refractive index of our mixture and guide the optimization towards realistic mixing fractions. Now let's create a lens to use this material. Under the Elements folder in the model hierarchy, select the default lens stack object. In its property editor, there is a table of surfaces. Click the Add button beneath that table to add a second surface, then double-click the Material column for the first surface to reveal a drop-down editor. Select the binary mixture material we created before. Then we'll double-click again to set the thickness for the first surface to 3 mm and hit Enter. We'll follow the same process to set the diameter of the stop to 14 mm and the diameter of the second surface to 15 mm. We will also set the clear aperture margin for the first surface to 1 mm to give a little bit of wiggle room for the off-axis bundle. We can see the lens we've created here in the model view. Left-click and drag will rotate the view, middle-click will pan the view, and the mouse wheel will zoom in and out. We can also use these buttons at the top of the model view to snap to different orientations and adjust other aspects of the view. I'm going to use the XZ axis button here to look at the lens from the side, and then click the axis toggle here on the right to prevent the axes from obscuring our lens. To run the simulation, press the F5 key on your keyboard, or right-click the reTORT simulation in the model hierarchy and select Run All. We see that this lens doesn't focus very well, so let's fix that and give our optimization a better starting point. Select the binary mixture in the model hierarchy, then set the C0 property to 0.5. Set the R² coefficient to 0.005, and then set the R⁴ coefficient to 0. Then rerun the simulation. That's much better. To run the optimization wizard, right-click the reTORT simulation and select Tools, Optimization Wizard. Or we could run it from the File menu by selecting Tools, reTORT, Optimization Wizard. We want to run a damped least squares optimization for this example, so select Local DLS Optimization and click OK. The optimization wizard will give us a list of properties we might want to optimize. In this case, surface curvatures, that is, inverse radius of curvature, the lens thickness, and our mixture coefficients. The wizard will also let us set the current values for these properties, as well as minimum and maximum values for the optimization. Click the checkboxes next to the two surface curvatures, as well as the N0, R2, R4, and R6, R8, Z1, and Z2 coefficients. These will be the properties that we optimize. In the Goals tab, we want to optimize for a back focal length of 40 mm, and we want to minimize the spot size. The Optimizer Settings tab lets us configure settings for the optimization algorithm. Note that by default, damped least squares does not adhere to the min and max property values. However, the default DLS settings are fine for us, so click the Run Local button to start the optimization. We can see the progress of the optimization here in the status dock, as well as the best cost the optimization has found so far. If we want to stop the optimization partway, we can click the Stop button next to the progress bar here in the lower right corner. Now that the optimization has completed, we see that our lens focuses much better at the focal plane. If we want to hide some of these rays to get a cleaner view, we can do that by clicking the Ray Bundles button at the top of the model view and selecting Meridional under Show Ray Planes. Then we will only see the meridional rays. Here is the focal drift plot for the GRIN singlet that we designed. We see that the lens is achromatic, with both incident angles having a focal shift of roughly 70 microns between the 450 and 700 nanometer wavelengths. This focal drift is much smaller than the achromatic triplet. This singlet also has a much smaller volume than the original triplet, so we have successfully reduced its size and weight by utilizing reTORT's gradient index material mixtures.